Okay, so Lewis dot structures. We spent a lot of time looking at the atom, how the electron behaves in an atom with quantum mechanics. Now when we get to molecules, the payoff is how we can put those atoms together to make molecules. And to do that, we use Lewis dot structures. Now what I'm going to go and do in this example, set of examples I should say, is work through a bunch of different structures, because that's the best way to learn how to do Lewis dot structures. Rather than reading too much about the theory, just go ahead and start drawing some structures and it'll work itself out. And in no particular order, I'm going to start with Ammonia Nh3. Now, you should have a periodic table with you at all times when you're working on Lewis dot structures, preferably not when it's all crumpled up. And the reason why you need this, Lewis dot structures focus on the valence electrons of atoms, the outermost s and p orbitals. Therefore, we need to know how many electrons are in those orbitals. Nitrogen will have 5 valence electrons, 3 hydrogens contribute 1 each, so that's 3. So that gives us a total of 8 electrons to work with. By convention, the first atom in the structure is almost always the central atom. If it's not, you'll be told that. The only other exception to that rule is with certain hydrogen compounds, like H2O, water, which we'll look at in a second. But everything else, the first atom is central. Hydrogen can never be the central atom. So, with that said, we've got a nitrogen, and it's bound to 3 hydrogens. I'm going to just draw this symmetrically, even though when we get to Vesper structures, molecular structures, we'll see that there's a better way to draw this. We have a central atom, terminal atoms, but they have to be connected with covalent bonds. So 2, 4, 6. So we've used 6 electrons. And we have 2 electrons that are left over. Hydrogen does not have to obey the octet rule, but nitrogen does. So we put a lone pair on the nitrogen. Now we've used our last 2 electrons, and we have 0 electrons. Typically, when you see ammonia, its structure, its Lewis dot structure, will be typically drawn just like this. These 2 are equivalent, but this looks a little bit cleaner. And we'll see that when we look at the 3-dimensional structure of the molecule, this is a much closer representation to the 3-dimensional than this. But from a Lewis dot structure point of view, they're both fine. If we look at formal charges, I'll use the bottom one. We calculate formal charge based on the number of valence electrons that we start with, which is 5 for nitrogen, and the number of valence electrons that are either on the atom or shared between 2 atoms in a chemical bond. 1, 2 from the lone pair, 3, 4, 5 from the chemical bonds between the hydrogens. Formally, the way you should do it is 2, 4, 6 times 1/2 is 3, 4, 5. I like to just count rather than make it into a big math problem. The result is 5. Therefore, the formal charge on nitrogen is 0. The formal charge on the hydrogens, and in this case all of the hydrogens are equivalent, hydrogen starts with 1 valence electron if it was a neutral atom. In this case, it's sharing one electron in a chemical bond. So that's just 1 minus 1. Also 0. Ammonia is a neutral molecule. So no formal charges is consistent with no overall charge. Sometimes we'll see in cases of formal charge, you can have a neutral molecule and the formal charges are non-zero, but they cancel out. Okay, on to the next one. Again, practicing Lewis dot structures. There's no easy way to get around it. If you want to do well on our final exam, well, you need to know how to do them. Now I'm going to do ammonium's structure right after doing ammonia, because they are related, obviously, but we can clearly see there's some structural differences. So nitrogen has 5 valence electrons. We now have 4 hydrogens, so that's 1 times 4. If I stopped here, I would have 9 valence electrons, but ammonium is a positively charged polyatomic species. It's got a +1 charge. Electrons are negative. A positive charge means I remove an electron. So from my electron count, I subtract 1 electron. So I go from 9 electrons to 8. Again, it's very easy to get confused of I'm counting electrons and I'm talking about charge. So always keep that in mind of we count up the number of electrons. If the molecule has a positive charge, we're removing electrons. If it has a negative charge, we're adding electrons. Typically, we'll see 8 or things that are divisible by 8 are very common. Not always the case, but that should, for small molecules, tell us something about the octet rule. We want to have 8 electrons. So nitrogen will be in the center. The hydrogens are going to be terminal. You don't get points added or subtracted for artistic interpretation. So I like to try and draw the molecule symmetrical, but if it was a little askew, it wouldn't make any difference. A covalent molecule needs to be bound together by, at the very least, single chemical bonds. So we put a single bond between each hydrogen and nitrogen. 2, 4, 6, 8. 8 electrons. Remember, each chemical bond is 2 electrons. Well, if I used 8 electrons, I now have 0 electrons. If we forgot about the charge, we would have 1 more electron here, and we'd have a problem. Because if we tried to put that 9th electron in the nitrogen or the hydrogen, we would violate the octet rule. So if you find yourself in a situation where you've drawn the molecule and you have too many electrons or too few electrons, it's usually because you made a mistake in the first step as far as counting the electrons. We're not quite done. Let's go back and do formal charge. This time I'll start with the hydrogen. A neutral hydrogen has 1 electron. I'm sharing 1 electron in the chemical bond. So each of the hydrogens in this molecule of ammonium has 0 formal charge. Seems reasonable. If we look at the formal charge of nitrogen, a neutral nitrogen atom has 5 valence electrons. In this molecule, there are no lone pairs, so we only count the bond pairs that it is sharing electrons with. So 2, 4, 6, 8 divided by 2 gives me 4. Or, again, 1, 2, 3, 4. Same result. whether you use the formal way they do it in the textbook or whether you just do it by counting. So we have 4 valence electrons that are being shared. 5 minus 4 gives me positive 1. Nitrogen has a formal charge of +1. The hydrogens have a formal charge of 0. So the overall charge of the molecule is +1. This is consistent. Ammonium is a charged species. That charge has to come from somewhere. And it comes from the formal charge on the nitrogen atom. If you have a charged species like ammonium, and you draw the Lewis dot structure, and all of the formal charges are 0, you've made a mistake, because that charge has to have some point of origin. In this case, it's the nitrogen. It is possible to have a molecule that has 0 formal charge, overall has 0 total charge, but the formal charges are non-zero, and that's because they can cancel out. And I will do an example of that in a moment. All right, silicate. It's not the most common polyatomic species. Silicon with 4 oxygens and a 4- charge. So, let's look at its Lewis dot structure. Silicon is directly under carbon, so it's going to have the same number of valence electrons as carbon, which is 4. Oxygen, XY, just to make sure that we're talking about oxygen, not 0. Oxygen will have 6 valence electrons, but there are 4 of them. So the total number of valence electrons donated by the oxygens is 4. 4 minus, we have a negative charge. It's -4. Electrons are negative, so that means we have 4 additional electrons. So we add 4 electrons to our total. And 24 plus 4 plus 4 gives me 32 electrons. Okay. Again, by convention, the central atom is first. So we're going to have a silicon in the center, surrounded by 4 oxygens. We need to have chemical bonds to hold the thing together, right? So 2, 4, 6, 8. So this gives us 24 electrons. Okay. We need that single covalent bond to turn this from atoms into a molecule. So now we have 24 electrons. What I like to do before thinking about multiple bonding is just put those electrons into the molecule as lone pairs and then go from there. So it's tempting sometimes to, in your mind, oh, this is going to need double bonds or triple bonds. Resist that urge, because once you've drawn a double bond, it's usually difficult to erase it, just because, well, you've got a double bond there. Why would I erase it? And if it's not correct, it'll make everything a mess. So 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now, why I went counterclockwise, I have no idea. It doesn't actually matter. So, 24 electrons used. 24 electrons are now 0 electrons. We've used them all. So now we need to analyze this structure in terms of the octet rule. If I look at the central silicon, 2, 4, 6, 8, it has an octet, so it's fine. If I look at each one of these oxygens, we have 2 electrons in the chemical bond, 2, 4, 6 electrons in the lone pairs. So that's also an octet. So we're happy there. Let's look at formal charge. Silicon has 4 valence electrons for a neutral silicon atom. It's sharing 2, 4, 6, 8. So if we divide that by 2, again, 1, 2, 3, 4, that gives me 4 electrons and a 0 formal charge. So the silicon, octet rule, 0 formal charge, it's nice and happy. Each of the oxygens is equivalent. So if we figure it out for one, we figured it out for all of them. Oxygen starts with 6 valence electrons for the neutral atom. It has 2, 4, 6, 7. One from the chemical bond. -1. Each of the oxygens has a -1 formal charge. The question to ask yourself, does that make sense? And hopefully you're saying yes. 4-. The entire molecule has a -4- charge. And that's from each one of these oxygens. Each one of these oxygens has a -1 charge. So -1 all the way around. So obviously I've made this drawing way too confusing now, but hopefully that makes sense. So the negative formal charges come from the oxygens. I'm going to do one more thing to prove a point. Now, in class, when we talk about formal charge, lowering formal charge is a good thing. If I can get rid of formal charge, that's great. The problem in this case, does that actually lower the formal charge? If I put in a double bond, well, 2, 4, 6, 8, the oxygen has the octet rule. I've expanded the octet of silicon, which is possible, but all I've actually done is move the formal charge now to the silicon, because the silicon would have 4 valence electrons minus 1, 2, 3, 4, 5. So now there would be a 0 charge here and a negative charge there. That's not a favorable structure because of electronegativity. Oxygen has a higher electronegativity, so it's going to want to have that negative formal charge on it versus silicon. So you could draw resonance structures with the double bonds, but they would not be as favorable as what we have here. Carbon monoxide, CO, is a relatively small molecule, obviously 2 atoms. Carbon is going to have 4 electrons. Oxygen is going to have 6 electrons. So now we have 10 electrons. It doesn't matter how you draw it because it's just 2 atoms, but by convention, we typically have it as CO, not OC, or up and down or any other orientation. So we have 2 atoms. We need to connect them. Single bond, 2 electrons. Again, now we have 8 electrons to work with. Again, put them in as lone pairs, just to start with. 2, 4, 6, 8. Just by inspection, clearly the carbon doesn't have an octet, right? 2, 4. That's a problem. I gave the oxygen octet, so it's happy. But we have to have an octet for our carbon. If we start playing this game of moving electrons around as lone pairs, Well, we'll see very quickly that doesn't work, because yes, now my carbon has an octet, but my oxygen does not. So once you reach that point where moving the lone pairs can't fix everything, now we have to look at multiple bonds. If I take these 2 electrons, put them into a chemical bond, 2, 4, 6, 8, the carbon is still obeying the octet rule, 2, 4, 6. Oxygen's getting closer. So remember, we don't have any more electrons to put into the molecule. We have to rearrange. So now we take the other lone pair on carbon and make a triple bond. 2, 4, 6, 8. Carbon obeys the octet rule. 2, 4, 6, 8. Oxygen obeys the octet rule. So from the octet rule, everybody's happy. 2, 4, 6, 8, 10. We've used all 10 of our electrons that we started with. Now we look at formal charges. A neutral carbon atom has 4 valence electrons. 2, 3, 4, 5. We have 5 here. So the carbon has a -1 formal charge. Oxygen has 6 valence electrons for a neutral atom. 2, 3, 4, 5. So 6 minus 5 is +1. Is that consistent? And the answer is actually yes, because +1 plus -1 gives me 0. Carbon monoxide is a neutral molecule. So neutral molecules can have formal charge. And in some cases, they'll just cancel each other. In that case, it would just cancel itself out. So the overall charge is 0. We cannot draw a better Lewis dot structure, because if we try and move any of these electrons around, we violate the octet rules. So we have to live with formal charge of +1 on the carbon, -1 on the carbon, +1 on the oxygen. So again, always go through looking at how many electrons you have, and then once you've satisfied the octet rule, make sure to calculate formal charge. Because in some cases, again, even though the molecule is 0, the atoms actually do have charge separation, formally. Okay, hydrogen cyanide. Now we've got a Lewis structure that's going to have 3 atoms in them. Hydrogen can never be the central atom. In this case, the way it's written, carbon will be the central atom with nitrogen as the terminal position. If there was any ambiguity of who was in the center, I would let you know one way or the other, either in the formula or I'd actually explicitly write it out. So let's do our electron count. Hydrogen has 1 valence electron, carbon has 4, and nitrogen donates 5 valence electrons, giving me a total of 10 electrons to work with. So we have a hydrogen, carbon, and a nitrogen to work with. They're going to be bound together by single covalent bonds. So that's 2, 4 electrons. So we have 6 electrons to work with. Again, go ahead and put them in as valence electrons, even if you know that's probably not going to work, just as a way to get the problem started. So 2, 4, 6. I have 0 electrons to work with, so I'm done. But of course, not quite. Hydrogen does not need to obey the octet rule. So 1 chemical bond, it's happy. Doesn't need lone pairs, doesn't need double bonds or anything like that. 2, 4, 6, 8. The nitrogen is okay as far as the octet rule, but of course carbon, 2, 4. If we move these lone pairs onto the nitrogen, again, when you're doing this, you'll find that you start to see trends. So you don't have to formally do this, but I like to do it just to prove the point. Well, 2, 4, 6, 8. Now the carbon obeys the octet rule, but the nitrogen does not. So clearly we need to have multiple bonds. A double bond, then a triple bond. Hydrogen does not need the octet. Carbon, 2, 4, 6, 8. 4 chemical bonds gives me the octet, so carbon is okay. Nitrogen, 2, 4, 6, 8. So nitrogen is also okay. Now let's count up formal charges, since we've got taken care of the octet rule. The formal charge on hydrogen is going to be 1 valence electron minus 1 from the chemical bond, gives me 0 formal charge. Carbon has 4 valence electrons for the neutral atom. 1, 2, 3, 4. So carbon is also 0. And it shouldn't be much of a surprise that nitrogen, which brings in 5 valence electrons, 2, 3, 4, 5, nitrogen is also 0. So everybody obeys the octet rule. All the formal charges are 0. That's consistent with the formula. So there we go. A triple bond and a single bond. So again, this is something that just with practice, you'll get used to realizing, well, wait a minute, this isn't going to work, so I need to start looking at double bonds, triple bonds, and so forth. We cannot have a quadruple bond. We can't have 4 chemical bonds in there. We can't move one of these one of these bonds over here to hydrogen, because hydrogen cannot have a double bond. So that's our best structure as far as the octet rule is concerned, and formal charge. Sulfur hexafluoride. Now we're going to start looking at molecules that inherently are going to violate the octet rule. But that's okay. When we move further down into the periodic table, where we have the quantum number equals n or greater, and that, if you're wondering what I'm talking about, quantum number equal what? Remember, on your periodic table, hydrogen to helium is n equals 1. Lithium to neon is n equals 2. Sodium to argon is n equals 3. So as we get to that row of the periodic table, we can start violating the octet rule. And the reason why is that at n equals 3, the quantum number n equals 3, we have empty d orbitals, and those can participate in bonding. So let's look at this molecule from an electron point of view. Sulfur has 6 valence electrons. Fluorine has 7, but of course there are 6 fluorines. So that's 42. There's no charge. So we have 48 electrons to work with. Sulfur will be the central atom. It's written first, and it has the lowest electronegativity. We have 6 fluorines. So we draw them around the sulfur. We're going to have 48 electrons to connect them. Even though this is obviously going to violate the octet rule, we have to put in our single bonds. So 2, 4, 6, 8, 10, 12. 12 is obviously not 8. But that's where we have atoms that can violate the octet rule. They have d orbitals. S, px, py, pz gives me 8 electrons, an octet, right? 2, 4, 6, 8. If I start adding d orbitals, well then I can violate that. I can have 5 chemical bonds, or I can have 6 chemical bonds, as in this case. So now we have 36 electrons to to work with. Again, the sulfur can violate the octet rule, but fluorine cannot, so it's going to need its octet. 36 electrons, we'll put them in as lone pairs. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. You don't have to count out loud like I am. As you can see, my electrons started getting weaker as I was running out of steam. Okay, so we put in all of our electrons, all 36 electrons that were left over from the chemical bonding. So, if I look at any one of these fluorines, 2, 4, 6, 8, it obeys the octet rule. So that's good. Let's look at formal charge. We start with the central sulfur. Sulfur has 6 valence electrons. It is in, change that so it doesn't look like a chemical bond. We have 1, 2, 3, 4, 5, 6 electrons that it's sharing in those chemical bonds. So its formal charge is 0. I can look at any fluorine. Look at this one since it's out of the way. Fluorine brings 7 valence electrons for a neutral atom. 2, 4, 6, 7. It also has 0 formal charge. So that's good, that's consistent. The only thing that is a little bit disturbing at first is the fact that the sulfur violates the octet rule. But that's acceptable. It's using its d orbitals to form those additional chemical bonds. And we'll discuss how that happens in what's known as orbital hybridization as we get into Chapter 8. So from a Lewis dot structure point of view, this is the correct structure. 6 chemical bonds, sulfur in the center, all the fluorines have an octet in the sense of 2, 4, 6, 3 lone pairs in a single bond. Okay, for the last 2 examples, I'm going to draw the Lewis dot structures of a few what are known as organic molecules. Organic chemistry is the chemistry of carbon, typically with carbon and hydrogen, or carbon, hydrogen, oxygen, or carbon, hydrogen, nitrogen, and a few other elements. But particularly, it's all chemistry focusing on carbon. And biologically active molecules are organic molecules. Typically. So, CH2O. Carbon, we'll see, is going to be the central atom. So carbon has 4 valence electrons. We have 2 hydrogens. And we have 1 oxygen, which is 6 electrons. So 4, 6, 12 electrons to work with. So I'm going to draw it like this, where the carbon is in the center, oxygen, hydrogen, so forth. If I rotated these positions, it actually wouldn't make any difference. 12 electrons, but we have to connect everything. So 2, 4, 6. So we've used half our electrons. Now we have 6 valence electrons to work with. Again, go ahead and put them in as lone pairs. Now, whether you want to put them on the carbon or the oxygen, I typically put them on the terminal atoms first. So that's 2, 4, 6. So I've used all my electrons. 2, 4, 6, 8. The oxygen's happy. Hydrogen doesn't need an octet, but of course, carbon needs an octet. If I move this lone pair down here, at this point you guys should see, well, that's not going to work because now the oxygen doesn't have an octet. So we're going to need a double bond. So we take that lone pair, Put it right there. Carbon has 2, 4, 6, 8 electrons. It obeys the octet rule. Oxygen has 2, 4, 6, 8 electrons. It's also obeying the octet rule. So from the octet rule, we're nice and happy. Let's look at formal charges. Hydrogen has 1 valence electron, is sharing 1 valence electron in that chemical bond, so it's 0. Carbon, a neutral carbon, is going to bring 4 valence electrons to the molecule. This has 1, 2, 3, 4. So that's also going to be formal charge of 0. Now we look at the oxygen. A neutral oxygen atom has 6 valence electrons. 2, 4, 5, 6. So everybody has formal charge of 0. They obey the octet rule, so we're happy. We're not going to worry about nomenclature in this course. That's what you have organic chemistry for. But just in case you're wondering, this is the molecular structure, the Lewis-Dot structure of formaldehyde, which obviously, if you've ever worked with any type of thing that you need to dissect, it's usually preserving tissue and other biological materials. So we've got our organic structure, but we're just using Lewis-Dot structures. You'll often see organic molecules drawn like this, where we have a carbon, hydrogen, and then some other atom, and then even another hydrogen. Why isn't it written CH4O? That seems like it'd be more condensed. The reason why, this actually is giving me a little bit of structural information. It's basically telling me I've got an oxygen with a hydrogen attached. Carbon is still the central atom, so that OH group is actually attached to that central carbon. So let's go ahead, count up valence electrons. In a molecule like this, I would explicitly tell you what the framework is going to be, or give you enough information that you can figure that out. So carbon has 4 valence electrons. We have 4 hydrogens, right? 3, 4. So that's 1 times 4. Oxygen has 6 valence electrons. So we have a total of 14 electrons to work with. I'm going to have my carbon in the center, and it's going to be bound to 3 hydrogens. 1, 2, 3. And then it's bound to an OH. Excuse me. So the oxygen will be here, and then the hydrogen will be here. It doesn't matter if you draw the OH going up, right or left, or down. It ends up being the same. Now here's the tricky part. We have to connect all of the atoms with single bonds. 2, 4, 6, 8, 10. Don't forget, with the oxygen, it has a chemical bond to the hydrogen. So that's 10 valence electrons. So we have 4 left over. If we look at the carbon, 2, 4, 6, 8. This carbon is actually very happy. It's got the octet rule. It doesn't care about getting any more electrons. Hydrogen only needs 1 chemical bond, so it's fine. But our oxygen, 2, 4, it's going to need an octet, which 2, 4. That just falls right into place. We have 0 electrons left over. So this gives me 2, 4, 6, 8 octet on carbon, 2, 4, 6, 8 octet on oxygen. You can go through and calculate formal charges of each one of these and prove that it is formal charges of 0. I'll do the math real quick. Carbon has 4 valence electrons, 1, 2, 3, 4 from the chemical bond. That's going to be 0. The formal charge for hydrogen, 1 valence electron, 1 from the bond, also 0. And then for the oxygen, because all the hydrogens are going to be the same, 6 valence electrons, 2, 4, 6, I'm sorry, whoops, 1, 2, 4, 6, almost miscounted there. That's why you want to be systematic. I was trying to take a shortcut. So 2, 4 from the lone pairs, 5, 6 from the chemical bonds gives me 0. So all of my chemical bonds are 0. This molecule is methanol. Typically when you see it drawn, you'll actually see it drawn like this, where it's rotated 90 degrees clockwise. Chemically, it's the same thing. So methanol is an organic molecule. It's in the class of molecules called alcohols. Methanol is wood alcohol. So anyway, both of these structures are identical. I've just taken this and rotated it to make it a little easier to see.